Hello everyone. In this session, we will be talking about fullrmc. Fullrmc is a framework for atomic and coarse-grained stochastic modeling. My goal here is to give you a general overview of fullrmc, and in the coming sessions, we will have more hands-on examples using the terminal and the web interface of fullrmc on the cloud. Please take notes of those useful links for fullrmc, for example, where you want to inquire for the cloud version of it, the open source version of it, the documentation, and a contact email. So before we start talking about fullrmc, I would like to put things at scale and briefly introduce the major atomic simulation techniques. So look here at the figure on the left. On the x-axis, we have the simulation time, and on the y-axis we have the simulation size, which is directly related to the number of atoms being simulated. At the very bottom left here, left corner, theoretical computations and also so-called ab initio computations take place. Just remember that even at the very basic level, for a handful of atoms and very finite simulation time, there is no exact theoretical solution. Just remember that the only system that is solved analytically is the isolated hydrogen atom. The moment this atom is not considered in total isolation anymore, which means having another atom nearby it, or a particle, or a photon passing nearby, those nearby particles will induce perturbations that perturbate the states of that atom, and it becomes impossible to solve the total system Hamiltonian, and perturbation theory is invoked, and one will start thinking about order of approximation, the first order, the second order, and the third order. In conclusion, everything is an approximation. In this world of simulation, everything is an approximation. And the more you attempt to go along the diagonal to bigger scales, bigger simulation times and sizes, the more assumptions and simplifications one needs to put in place in order to be able to compute the exponentially increasing complexity of the system. Up to a few thousands of atoms, and for short interaction characteristic times. Quantum mechanics approximations are computable. I'm talking here about this area. A bit further along here, for example, when we start talking about all atoms, it's definitely all atoms, but when we have thousands of atoms and up to 100,000 of atoms, classical approaches are used. Beyond that, more approximations needs to be put in place. Computation and algorithm tricks and techniques and coarse graining must be used. Keep in mind here that this kind of simulation is meant to reproduce the structure, dynamics of the system. So with this being in mind, one should always sacrifice one for another, which means adapting the force field and Hamiltonian to get better structural agreement at the expense of, for example, poor dynamics and vice versa. On the other hand, when we start thinking about reverse Monte Carlo, and that's what I'm showing here to the right, reverse Monte Carlo simulations is an all-atom technique that attempts to solve the structure of materials and not worry much about the atomic dynamics at all. This is proved to be a fine technique when the goal is to reproduce local structures and perturbations due, for example, to asymmetric atomic vibrations or orientations. Nevertheless, RMC suffers from the lack of unicity and is very limited in its power due to the nature of trying to find a complex solution by merely relying on random sampling. So without any further introduction, fullrmc sits somewhere in between those two worlds. It's not an RMC software. I insist on that. Fullrmc, despite its name, it's not an RMC, a reverse Monte Carlo solution. but a rather stochastic framework, not a software, it's a framework that allows you to specify the sampling all the way the atoms must be selected and move. Full RMC also allows you to simulate a mixture of systems, which is not possible in any theoretical all RMC approach, up to the nanoscopic or mesoscopic scale, and also enables elements coarse graining as well. It is simply impossible to explain all the details about full RMC in here. There's barely enough time for a swift introduction. My goal is really to get you curious enough to get started using the framework or full RMC, or whether that being from the terminal or from the cloud-based web GUI. All right, so before I dig into the details, let me tell you what the motivation was to putting full RMC together. Back in 2013, I was personally working on putting together a theoretical solution attempting to formulate a force field or an energy expression that explains the mid-range ordering happening in some battery cathode materials. So, a brief summary, those materials loses capacity with cycles between cycle 1, 16, and 38. And looking at what's happening at a structural level, there is some mid-range ordering happening right here that no one was able to explain. So this mid-range ordering becomes more and more prominent with each cycle of the battery, and there is no experimental nor numerical technique that can unravel the reality of what's happening. This problem led to thousands of publications, all of which were mostly being speculations about what's happening at the atomic level. The reality is, back in the time, I'm confident saying that no one knows what is really happening, and it's all speculations. After some time, I tried my best, but I realized that I was thinking about the problem all wrong, and that any energetic or a force field approach will fail because it's not possible for a single force field or a Hamiltonian expression to survive multiple phase transitions of a dynamically changing material. What I needed actually is a numerical and statistical approach that can allow me to explore any hypothesis or atomic structure I can think of, and that can also allow me to dynamically combine those hypotheses or atomic structures in order to find a plausible solution. And this is how I started thinking about full RMC. So look at this like TEM image here of the cathode material. There are some areas that are ordered, others that look more amorphous. We have some stacking faults, we have interfaces like here, we have dislocations, we have atoms taken out, insertions. All of that is probably what is leading to the mid-range ordering. There is no Hamiltonian that's solved for all of this. There is no force field that will capture all of that. There is no single box modeling that will be able to get you all of this. You need to be able to have a statistical solution to all of this. And that's what full RMC is about. All right. Now I will take the rest of this session to tell you to dig a little bit deep to get to the first layer of full RMC. In a nutshell, this is a simplified workflow of full RMC engine. Notice here that I have add frame. We will talk about this later, but focus on the green arrows. At each and every step of a full RMC run, the selector will be invoked, something called the selector, we'll talk about it. And the selector can recur, and the selector can train itself using certain machine learning algorithms. Then the selector will select a group, and that group can get a subset of itself. We will talk about more, but just know that a group is a set of atoms. And each and every group will have its own move generator. All right? So each group can move it in its own way that you can specify by yourself, and it can be aware of its neighbors as well. And then more so, you can add chemical constraints or rules. Those can be energy terms for bonds, for van der Waals forces. Those can be first order approximations for angles, dihedrals, and impropers, all of that. Those are the chemical constraints. When a chemical constraint is unlikely to happen or broken, the process stops and fullrmc's engines go back to the initial step of the selector. If that process is approved, then the next step would be checking on the experimental constraints or the experimental observables that you are going to be providing. Then the last step is computing the loss function. The loss function, there is a plethora of losses implemented in fullrmc. Some of them are machine learning enabled that will be trained during runtime, and some of them, actually all of them, can allow loss function warping. We will talk more about this in the coming slides as well. So once the loss is computed, a decision has to be made whether this selection of that group performing that type of move should be allowed or not. And then that's a loop. So this looks kind of similar to what an RMC solution looks like, with a lot more details and a lot more additional things that are happening in between, especially the frames and how the frames interact. So you can have multiple frames that solve for the same system, all interacting at the same time to provide a unique solution. Now let's talk about groups and move generators. Just to tell you what's going to happen, I'll be talking about each and every one of those steps along the way. So let's talk about groups and move generators very swiftly. Consider this as an atomic, an atomic structure. This is actually a frame that can have thousands of atoms, up to hundreds of thousands of atoms. The red dashed lines are groups that you as a user will create and specify. So you can create a group of one atom. You can create groups that contain a full molecule or a full unit cell or a full polyhedral. You can create groups of atoms coming from different molecules. It's really structure agnostic. And then for each and every group, you will be specifying how this group shall move, how this group shall explore this space. This is the stochastic nature of fullrmc. Stochastic because it's not purely random. So you can have the group translate, random translation along an axis or towards another group or towards certain cluster of atoms. You can create rotations, orientations to orient molecules towards each other or to rotate the unit cells in a crystal structure. You can agitate, for example, certain bonds, angles, dihedrals. You can create swapping. You can dynamically remove atoms from the system. You can also have a group being aware of its environment and let, for example, atoms attempt to get closer to each other. Those are representations of move being generated. For example, here I'm allowing this molecule to go to translate, doing also rotations towards its neighboring molecule. This is a translation along a certain x-axis. These are agitations of the bonds, for example. The number of moves that you can create is infinite. You can imagine any move that you think it's likely to happen, or it's likely to get your system to a solution, and you can make it happen in fullrmc. You are not going to be relying on randomness anymore. You can if you want to, but that's not the goal. All right, for selectors. The selectors is the way the engine is going to be selecting those groups during runtime. So The easiest selector you can think of is a random selector. That's reverse Monte Carlo selector. Then you can have a selector that will select more groups more often than others. This is a weighted selector. You can define selectors with defined orders. You can define selectors with directional orders. So if you want to expand the system or contract the system, you need to start moving atoms from the outer layer first. You can also have selectors that would learn what to select. Here we are using a reinforcement machine learning implementation to do so, and we prove that for a good bunch of simulations, this selector will get you to a solution faster, and that's the ratio of accepted steps that will go along the way. As far as constraints, this is a non-exhaustive list of constraints that fullRMC offers. The distance constraint, which is a van der Waals constraint, the bonds between two bonded atoms, the angles, the dihedrals, the improper, the atomic coordination numbers. So as you can see, it's really structure agnostic. You can be in a system of molecules, in a system where you are simulating a pure crystal or a mixture of models, and you can use all of that. And you have 6 different implementation of experimental data: pair distribution function, radial distribution function, pair correlation constraints or function, and that depends on the flavor or your preference and your experimental data, and you can shuffle between all of those, absolutely. Now let's talk about the distributions of fullRMC. There are 2 types of distribution for fullRMC. You have the open source distribution that you can find on GitHub. And this is the only distribution that was available so far for many of you. You can use that distribution from the terminal, or you can use that distribution to create a Python file and run it. A full online documentation, exhaustive online documentation, you can find on github.io. The link is right here. And there is also a question and answer forum where you can ask your questions, and I will make sure to answer it, if not me, someone else from that forum. There is another distribution for fullRMC that is only available on the cloud, and it provides you with a super human-friendly graphic interface with a nice atoms visualizer and plotting tools, and you can do everything that you can do from the terminal. You can do it in this web interface in here. In addition, it leverages new technology that is patented technology called soft grid that allows fullRMC to make full use of multiple computation units at the same time, run faster, and do statistical computations, mesoscopic computations, nanoscopic, and coarse-grained computation. This version is way more advanced than the one that you see on the cloud, on the open source version on GitHub. And it also provides a graphic interface. I will demo it as well. All right, and if you want to see what soft grid is, you can check it out in here. This is it's a patented technology. It's not open source, and we cannot distribute it along with the open source distribution of fullRMC. All right. Now let's get into some examples. I will be showing you here code snippets, and I will be explaining those code snippets. And fear not, in the coming 2 sessions, I will be giving you real hands-on experience of fullRMC using the terminal, and I will do the same using the cloud service. Those code snippets, if you copy those, they will run. If you have fullRMC installed, this will run fullRMC. It's not just something that you cannot use. So let me go line by line and tell you what it is. As I said, fullRMC is a framework, it's not a software. You're not going to be creating a parameter file that is proprietary for fullRMC that you can learn and spend time learning. You will be using Python, period. In the backend, fullrmc interfaces its C compiled core with Python. So the only programming language you have to deal with is Python. And this is as simple as it gets. Using the terminal, you can import the needed modules. For example, here from fullrmc.engine import engine. So currently I have the engine implementation ready. I can instantiate the engine. So engine equal engine, and then I give it a path, which is where I want to save this engine on the disk. Then I can read an initial structure. fullrmc can ingest PDB files, can ingest CIF files, XYZ files, or you can build your own crystals using the fullrmc's crystal builder. And then you would run the system. So those 4 lines are enough to run fullrmc. The only thing here is that you didn't touch the groups, you didn't create your own groups, so it's all the default settings. You didn't even add any constraints. So what's going to happen is you're going to destroy your structure right away, because there is no constraints, there are no rules, everything will be going left and right. But that works. Now we need to add on top of it. Let's set up some constraints. The same thing, import everything that we need. From fullrmc, I'm importing the atomic coordination number constraint, the pair distribution constraint, the intermolecular distance constraint. This is an old implementation. It's still useful, you can still use it. Currently, the current implementation is simply distance constraint. But either way, I'm importing the reduced structure factor constraint. You can see the formulae of these on fullrmc's online documentation. The same way, instantiating the engine, setting the initial structure, creating those constraints one by one. For example, here I'm creating the atomic coordination number. I'm setting the coordination shells one by one. I'm setting those by definition. Then I'm creating the intermolecular distance constraint, and I'm not setting anything. I'm leaving everything as a default just for the sake of that example. Then I'm instantiating a pair distribution constraint, which is your experimental data, given that this is the right path to the file where you saved your experimental data. And I'm telling this constraint that this is for X-rays, atomic number. And I'm doing the same for reduced structure factor. Then add those constraints to the engine and run the engine. Engine.run, number of steps, save frequency, and so on and so forth. Doing this is enough to run fullrmc, and by doing that, just that, you ran an RMC simulation, not a stochastic simulation. So this is all what it takes to run fullrmc in pure random mode. What's going to happen next is up to you to discover, and I will take you along the way to show you how you can go ways and beyond pure randomness and start making use of fullrmc. So the next step is, let's set up a different group selector, not a random group selector, and let's have this selector select the groups in a recursive way. Very important property. So also, I'm not going to copy the code from above, but I am importing here 2 new modules, recursive group selector and directional order selector. What directional order selector will do, it will select the groups based on their position relatively to a center. You can compute that center and assign it to this directional order selector. For example, here I'm computing the center as the geometric center of all the atom's coordinates. Then I'm creating a directional order selector. I'm giving it a center. I'm telling it to expand, which means when you read the documentation, it's going to be selecting groups from the outer layer down to the inner layers. And then I'm also telling it to adjust the move generators for each and every group. What that does, it will automatically change the move generator for the groups to a combination of rotations and translations that will expand the system away from the center. That's all what it does. You don't need to do that. You can do that manually and set up new move generators yourself. But this is a helper flag. Then what I'm doing, I'm taking that group selector and I am wrapping it with a recursive group selector here. You see that? RGS equal recursive group selector, and then I'm giving it the group selector. And what this does, fullrmc now is going to recursively select the same group 20 times before selecting the next group. So each time I'm selecting a group, I'm selecting it 20 times, 20 steps of the engine runtime. This group will be selected 20 times in a row, and a move will be attempted 20 times on that group before selecting a new group. So I'm giving it more time and more chance to move and to go out of its minimum. There are two flags here, refine and explore. Very important flags. Those flags are very important when set to true to take you out of local minima, and I'll show you a slide video about that. Then take that group selector, setting it to the engine, and run. That's all what it takes. That's a framework. You are invoking API calls like so, and then setting those to the engine, and then you run it. So here, let's also do atom swapping. I don't want to do translations. I don't want to do rotations. I want to swap atoms. In this system, that's a nickel titanium memory shape alloy. I know I have two elements in that system, nickel or titanium. Let's do swapping between nickel and titanium. Again, the same way, import swap position generator. And then I'm creating two lists or two arrays of atoms. The first one will contain the nickel atoms indexes, nickel swap list. The second one, the titanium atom indexes, titanium swap list. Then I'm creating two different move generators. The first one that I call two nickel swap generator, where the swap list is the nickel swap list. The second one, it's a two titanium swap generator, where the swap list is titanium swap list. So if you're following, now I'm looping through all the groups in the engine, and when the group atom is nickel, I'm setting the move generator for that group to two titanium swap generator. Otherwise, if the group atom is titanium, I'm setting the move generator to a swap generator, which is two nickel swap generator. So during engine runtime, when a group that contains nickel in it is selected, the move generator is a swap generator to titanium, and randomly a swap will be attempted between this group or this nickel and one of the titanium from the titanium swap list. Now I set up the swap position generators, I can run the engine, and I can even do things even way more complex. I can combine move generators for the same group. I can collect those. I'm not gonna get through all of those details, but you can see all of those online. There's a lot of videos that I put online for you to learn from. Let me here show you what explore mode is. Those are videos that I provide in the documentation. But I decided to show you two of those videos, which is for the explore and how you can create move generators to dock two molecules on top of each other. Keep in mind, this is structure agnostic. I'm choosing molecules that can be a crystal structure or anything else. You can find all of those videos on YouTube. You can search for fullrmc-saas, go to that playlist, or that's the link to the playlist, or you can search for the tutorials in YouTube by searching, again, fullrmc-saas dash, and here you have the title, whatever the title is. If you just put fullrmc-saas, everything will show up in front of you. Everything that ends with tutorial in a bracket would be a tutorial, would be a long movie on YouTube. Everything that ends with short clip would be a short demo clip. So now you know it. So let me play this a little bit. And all right, I'll pause it a little bit here. This is a real simulation in fullrmc. And you can find it in the set of examples I provide. That shows the difference from normal reverse Monte Carlo and exploring stochastic engine. So let me move it a little bit more to show you what this is. All right, beautiful. The black dot here is the current state of an atom or the engine. The dashed lines is the maximum distance that this atom is allowed to move left or right. So I'm doing the same simulation for both. And you can see that this system will be stuck here because there's no way that you can go up, left or right. I didn't mention that this is the last curve here. So let me move it a little bit further. All right, so the traditional reverse Monte Carlo here is stuck because this is the minimum on the loss. Even if you will allow certain steps to be accepted, the system will drop back. It's very unlikely for this position here to go beyond that huge potential spike. But in explore mode, what explore does in fullrmc, imagine that now your system is two, the real one and an avatar structure system. And the avatar will go and explore the space unless a chemical or a physical constraint is broken. If not, the avatar will go and explore the lost space until the avatar finds a better position. And let me show you that here. So that's the avatar. It's going, boom. Now the black dot followed because it's a better position for it. The avatar keeps exploring, left and right, going left and right, but the system is here. It's not going anywhere. Now the system followed because that's a better position. And that's what explore does. And if you are not in an explore mode, you are stuck. And keep in mind, this looks simple in 2D, but this is not in 2-dimension happening in fullrmc. It's happening in the 3-dimensional space, in the hyperspace of the loss function. That's a difficult thing to do, or to achieve in random motion. Now let's talk about move generators. Let's assume I have two groups. The first group, that is this one, it's a molecule. That's the other group. I want to try to dock this molecule on this one. If I want to adopt a random motion, it's probably going to take me an infinite time. I need to be able to tell this molecule to be able to move toward this one. Again, this is an example provided in fullrmc. You can run it yourself, but that's what's going to happen. I'm telling this molecule to translate toward this one and orient itself to this molecule as well. And that's how fullrmc engines work. You are not counting and hoping that randomness will get you where you need to be. You are stochastically exploring the space. Very important. So to get out of local minima, you can do selection and recursion in selection. You can do explore and refine modes. You can allow a smart loss function in fullrmc that is machine learning enabled. I'm not going to talk about it here, but you can look it up online. You can also allow loss warping, which is a new technique to warp the loss function in a way that your system will continuously evolve to a better place. Also, you can help your system to get or to test your hypotheses, not by pure randomness, but you can tell your groups how to move, whether in translation, rotation, orientations. You can align, you can move planes, you can move rods of atoms, you can dislocate, you can create stacking faults, you can remove atoms in and out dynamically, you can move polyhedral moves, unit cell moves, molecular moves. All of those are available in fullrmc, and you can run them in the free version that you can find on GitHub. All right, so far we've been talking about a system and trying to simulate the infinite of a system in what is called a periodic boundary conditions. So we are simulating the continuum of a system. But what would happen if, and this is a real scenario where we are simulating or we are measuring the isolated state of the system. The way we do that in general is we will be measuring a system in solution, then we will measure the solution by itself, and we subtract the two signals, and we end up in an artificial kind of experiment where we isolate the nanoparticles, for example, in solution. And if the solution is dilute enough, it's going to look like as if we are measuring isolated systems. So how does fullRMC take care of that? The way fullRMC does it, fullRMC is able to simulate both scenarios. The continuum is simulated by the so-called periodic boundary conditions. The isolated state is simulated by so-called infinite boundary conditions. Maybe the terminology is funky here, but infinite is because the boundary conditions are set at the infinite. So you are simulating an isolated system. The way fullRMC does it to account for the drop in density is by computing a sort of a shape function that will be subtracted to bring back your simulated system to the experimental one. I'm not gonna go more into the details, but I really advise each and every one of you to check what a periodic boundary system is. You can Google or YouTube this video, fullRMC Advanced Viewer. You can scroll to minute 1836 and watch 20 minutes from there, so up to 36 minutes maybe or so. That's the link, and this will show you in details what periodic boundary conditions are visually. You will see that while interacting with fullRMC, how you can achieve all of this. I really recommend you all to watch that. All right. Finally, maybe this is gonna be the last example I'll be showing here. This shows you how to dynamically remove atoms. I'm not gonna throw here code that would be part of the examples that are provided in fullRMC, but this is another battery material where we have rings of sulfur. That's a lithium sulfur battery. And the hypothesis is that some of those rings will lose their sulfur atoms, and we have sulfur chains now that are of a length of 2, 3, 4, 5, 6 sulfurs. So the way we do it, we did that in fullRMC, and that's a published work. We started simulation from a full ring system, and we dynamically moved those rings until there's no possible move that allows us to fit the system, and then we started removing atoms out. And by removing atoms out, fullRMC by itself automatically breaks the bonds and account for that in the constraints, and you start creating chains in the system dynamically, and then moving those chains along until we get to a normal fit, to a good fit of that system. This might not be the only solution for that, but that's one, and in fullRMC you can attempt so many others as well. All right. So I know maybe we spoke a lot already. What is fullRMC and how is it working? fullRMC, again, it's a framework, and when you save a fullRMC engine in your computer, you're not going to save one file. You're going to save a directory, and this is using a certain repository technology here. So, for example, that's an engine, tutorial nanoparticle size distribution. And those are the files and folders in that engine. And each folder here is a frame, and some frames are multi-frames that contain other frames. All right, we can talk more about that later. So, what is a frame? A frame in fullRMC, you probably don't need to use it in fullRMC, but if you want to use that, I advise everyone to use that. In fullRMC, you would be running a simulation in a frame. By default, fullRMC creates frame 0. So let's say this is your initial structure sitting in frame 0. and you want to move it a little bit or do whatever you want to do with it, then you want to attempt doing certain translations. But using the frame technology here, you would be able to restore an old system or an old fit whenever you need to. So let's say you want to do some translations, you create a new frame, you do the translation all there, and then you don't want to lose this snapshot. You want to do something else and being able to return to this snapshot. You create a new frame, then you copy this one to that one. Now you have this saved. You can always return to that frame anytime you like. And then you apply different moves. For example, here I'm moving atoms towards each other. I'm not doing just random translations. Then I like this state of the system. I want to do another one. I want to try doing swapping. I don't want to lose what happened here. So I create another frame. I call it swaps, for example. And then I start doing atomic swaps. Maybe I like the final result, maybe not. If I like it, I'll keep it. If I don't, I can delete that frame or do whatever I want to do. This is just like a code repository, but for atomic systems. And it is also used to do the supercomputing. It's not just for that. Multi-frames are used to do supercomputing. You're not going to be using it on your machine. On your machine, you will be using simple frames like that. But for supercomputing, that's what is used, leveraged by SoftGrid. Alrighty. Now, let's go fast around this and how, if you remember the battery problem I spoke about at the beginning, how I can simulate this in fullrmc. So considering this structure here, I can create multiple frames. Each one of them will be reproducing one part of that structure. It's like a mixture of models. And then I will run all of those in parallel to create a single solution. So this is some difficult computation that happen in fullrmc, where at each and every step of the engine, all of those frames are communicating with each other, and the ratio of contribution of each and every frame will be communicated. This is the so-called mesoscopic computation. We will talk more about this. That's another example of the mesoscopic computation, where let's say we have a solution of nanoparticles. We don't know what the distribution of those nanoparticles are. In general, what we do, we assume a normal distribution. But who says that's always the case? Sometimes we have two normal distributions in the solution. So how we do that? The same way. We create a multi-frame, we create multiple sizes of this nanoparticle, and we let fullrmc run the mesoscopic computation and find out the real distribution of those nanoparticles. So I will stop here. I appreciate you listening to me so far, and we will be doing hands-on tutorial next. Thank you.